Okay, so we are talking about antiderivatives. You have your book that you want to make sure you're opened up there so you can follow along. We've got some great pictures here on 4.9. So it says the goal of differentiation is to find the derivative f prime of a given function f. The reverse process is called anti-differentiation. So we went from f to f prime. Now we are going from f prime to f. So this was called differentiation. This process, anti-differentiation. This term right here was called the derivative. Now, what I would call the original function is the antiderivative. We noticed patterns here. We're going to utilize that as a pattern for the antiderivative. Okay. Later on, towards the end of this lesson and the beginning of the next lesson, we'll find out that the antiderivative also goes by another name,
Integral.
the integral. And it represents the other half of calculus, so to speak. Everything in calculus, at least in Calc 1, Calc 2, it's the derivative and the integral. It's doing everything forward and then going everything backwards. And just like in all other aspects of math, where there is constant good and evil fighting each other, always destroying each other, addition, subtraction, multiplication, division, taking the square of something, taking the square root, e to the x, ln x, always fighting, never resolving everything, just always reducing to 0 or 1 or whatever. You have differentiation, like functions, and then the inverse functions. See, it's like a superhero, supervillain, right? Always completely opposite. And the supervillain is always much stronger, right? Just always kind of the way it is. Division is always harder than multiplication. Everyone loves addition but hates subtraction. And that kind of holds here true as well. Everyone kind of likes differentiation, but anti-differentiation just kind of makes your head hurt, all right? And it's not as pretty, it's not as fun, but it's really powerful. This differentiation helped us find information about rates of change. What else did it help us find out?
The slope of the tangent.
Yeah, slope of the tangent line. It helped us learn information about when the function was increasing or decreasing, concave up, concave down. Gives all sorts of applications here, okay? And there are all sorts of applications here of doing the antiderivative. The big one, and the first one that we end up talking about, is the area under a curve. Okay? And then there are a ton of applications in physics. And when I mean physics, I don't just mean like the area. Well, we'll find also that there's some volume, which are pretty readily obvious. But there are lots of times in physics when you're going to add up an infinite number of things and things like that. And that the relationship is the antiderivative. So, primary application of calculus is physics. That's just the way it is. So, let's go ahead and start thinking backwards. So, I'll put the original function here and then the derivative down here. And y'all help me out here. Okay, so x squared, so that's the function. The derivative is, call it out to me.
2x.
2x. If it was x cubed, the derivative.
3x squared.
3x squared. What if it was like 5x to the 8th?
40x to the 7th.
Yeah, I'm going to write that as 5 times 8 times x to the 7th. Or if you had any sort of, x to the n, then we had...
it would be nx to the n minus 1.
Mm-hmm. All right. So now what we want to think about is going the opposite way. All right. If I give you 2x, how would you get back to x squared? remember when we went this way, we had the pop down, power down. We would take that, we would pop down the 2, made the coefficient, and then we would power down, change that 2 to a 1, right? So what about if we're going from this step to this step, if we're going from 2x up to x squared? Well, we are, if you know, I've got an imaginary 1 right here. We're kind of doing the opposite operations in the opposite order. I'll say again, for the opposite operations in the opposite order. So instead of going power down, we're going to power up. All right? And instead of taking that number and multiplying it times the coefficient times the x, we would be dividing it. So observe, here's 2x to the first, okay? I'm going, I still have 2x, okay? When I'm bringing it up here, I'm going to power it up, so 1 to 2, and then instead of bringing that 2 out here to the front, I'm going to divide it. Divide this whole term by that. And when I do divide that whole term, then those 2 cancel out. Alright? Because this, you still have this 2 here. Alright? So we're thinking sort of like a power up, divide up. I don't know, what's the opposite of pop? Down. So, power up, divide up. I don't know, that's really kind of weird, but okay. Let's see if that holds over for this one. So 3x squared. Going up this way, this is the derivative, finding the original function, or finding the antiderivative. So power up, so the x squared turns into 3x cubed, right? So powering up, and then divide up. So divide it, and those 3's cancel out, and lo and behold, I end up with the x cubed. Let's try this one. We had, it was originally, like what Ivan said, 40 x to the 7th. Okay, for our derivative. So 40 x to the 7th. So I'm still going to write the 40, still going to write x. Power up, we get 8. Divide up, divide by 8. 40 divided by 8 is 5. 5x to the 8th.
So we divide by the power.
By the new power.
Yeah.
Yeah. Okay. So let's say I have x to the n right here for the derivative. Going up this way, it's going to be x to the
n plus 1.
N plus 1. That's the power up.
Over
then
n plus 1.
Over n plus 1. Yeah. It's definitely something worth writing down. So I'm going to write a couple problems here, and we can try your hand at finding the antiderivative. So let's go x to the 4th. Let's go 8x squared, and I don't know, 20x cubed. And I want you to find the antiderivative. These are the derivatives. And I want you to find the original function. And put it on paper. What's going on here? All right, Harley, you're up first. Antiderivative of x to the fourth.
The 4x to the third.
Nope. No, that would be the derivative.
Mm.
We're doing the antiderivative now. So we're going to power up. Divide up over that number. This is the derivative. So this is like the second row.
Oh.
Okay? And we're going to find the antiderivative, or find the original function. Okay? So what we're doing is we're applying this formula right here, x to the n. So power up the exponent, and then divide by that new exponent. And if you're not sure, how do you check your work?
The derivative of the one on top?
Yeah, take the derivative. Let's check it. What's the derivative of this? Pop down, 5, power down, x to the fourth, all over 5. Well, the 5 over 5 would cancel, and we'd end up with x to the fourth right there. Alright, let's do this one in stages here. The 8 stays in front. Okay? Power of x turns into what, Ivan?
3.
Yep. X to the third divided by
3.
3. Then you ask yourself, can I simplify that 8 over 3? And the answer is no. Check your work. Going from the function down to the derivative. So pop down, we would pop down the 3, which would then cancel out the 3 in the denominator. Power down, the 3 would turn into a 2. So we end up with 8x squared. All right, Harley, your turn.
So 20x to the fourth over 4.
Yeah, there we go. She's got it now. 20x to the fourth over 4. And then we'll simplify that. 20 over 4 reduces to 5 x to the fourth. We can check that. Am I in the frame there, James? Check it, take the derivative, pop down, so 4 times 5 is 20, power down, x to the 4 turns into x cubed. I'm going to show you a notation for this, okay? But not quite yet, because I need to tell you the other side of the story on this, okay? So I am going to show you a notation momentarily. Any questions? Do we need to do any more? We feel pretty good at antiderivatives. I don't expect you to feel really good. I expect you to know how to do it. Okay. Well, Ivan knows where we're going with this, but we got to do it anyway. Let's play a little game here. I'm going to give you some more original functions, and then we're going to look at the derivatives, okay? Swing me back over there. James, thank you. All right, let's try x squared. So these original functions, I want you to find the derivative. Harley, you're doing x squared. Ivan, you are doing x squared plus 5. And James, you are doing x squared minus 3. You have 5 seconds to tell me the derivative. 4, 3, 2. Okay, so, alright, so his 2x. Harley?
2x.
James?
2x.
Yeah. Okay. So, what if I give you a problem that I say f prime of x equals 2x. Find f of x. Right? Seems like a legitimate thing. We were just kind of doing that over there. So we're like, all right, no big deal. 2x, I'm going to go up to the original function. So I'll write the 2 there. Let's power up. So x to the first turns into x to the second. And then divide up. So divide by 2. So there we go. The answer is x squared. Right? using our rule, our antiderivative power rule, we've determined that the antiderivative of 2x is x squared. In which case, Harley, we were able to arrive at your answer, going the opposite way. The problem is that's not the only answer, because the antiderivative of 2x is just as possible to be x squared plus 5. And the antiderivative of 2x could also be x squared minus 3. In fact, there's even more of them that I could write down here, right?
An infinite.
I could write an infinite number of functions for the original function there, for the antiderivative. It could be x squared plus 4, it could be x squared plus 3, it could be x squared plus 4.1, x squared plus 4.2. See where I'm going with this? It could be x squared plus 4.4, x squared plus 4.5. Are you getting it yet? Or I'm going to do some more examples. X squared. So, right. So the antiderivative, unfortunately, is not sort of like a one-to-one matching situation like you have with the derivative. The antiderivative could be any of these guys. So here's what we do. When we're trying to find the antiderivative and we find out that it's x squared, we say, all right, here's your answer, find f of x. Well, f of x is equal to x squared, and we need some way of denoting that it could be plus 5, minus 3, plus 20, minus 10, plus 4.4, whatever, and that's why we put plus c, where c is what's called a constant of integration. It means, I don't know what number that is, it's going to be something, but I know that it could be any one of those numbers. And that number is a constant, it is not a function of x. There's no 5x here or 3x here, because if there was, then that would affect our derivative. So we'll put a little arrow to their c and have a new vocabulary term here. Constant of integration. And now we are ready for our new notation. So previously in calculus class, the notation for indicating I'm taking the derivative of something would be something like this. So the derivative with respect to x of, x squared equals 2x. Now, this says new, kind of, but I guess it's the same thing. The notation for the antiderivative is as such. A long, sort of capital, stretched out, slender s of, we'll say, 2x. And then we put this dx right here, because x is my variable of integration, equals x squared plus c. That's the notation. And so now we'll do some labeling here. So that's the integral symbol or the antiderivative symbol. So you can say whatever you want. I'm going to say integral. Integral of 2x. So you have some sort of function rule here, some sort of formula. It has a technical name. It's called the integrand. Dx is, well, we talked about differentials. It means an infinitely small region along the x-axis. We're not really tying any of this to graphs at this point. So you can say, well, this is letting us know that it's with respect to x, okay? Or that x is our variable of integration, all right? So this, I just call it dx. So everybody calls it dx. But we sometimes I'll say with respect to x, and at some we'll change these values up here at some point, and you'll see that it doesn't really, what the difference is. But so the integral of 2x with respect to x is equal to x squared plus c. We already talked about how the plus c is the constant of integration. So let's just go ahead and get used to this new notation here, shall we? So the antiderivative of, we'll do something different, 8x cubed dx equals, we'll keep the 8, the x cubed turns into an x to the, say it again? Fourth over 4, and then always put your plus c. And then we can do a simplification. 8 over 4 is 2, so 2x to the 4th plus c. You might say, oh, I'm not going to write the plus c at the very first step. Write the plus c the first step. Okay? I had a former math teacher here, super smart guy, and he said, he would always tell how in Calculus 2, he had a quiz, and he got every single question right. He went to SWAU over here, and but he forgot his plus c, so he got like an 80 on the test, or on the quiz, or whatever it was. And he's like telling the professor, like, look, I got all this stuff right. And the professor, like, you forgot the plus c. You're not correct. Or, I don't know if it was an 80, maybe it was a 90, or something like that. And so from then on every single calculus, quiz, test, or whatever homework that he did, at the very top he wrote, put plus c, like the student did, like the guy who ended up being a teacher here. So yeah, he would put plus c up there at the top, so he would always remind himself to put that on there. So, okay. Let's do one more. Integral of, do something ridiculous. 17x to the 20th dx. James, in your head, what's that going to be?
17x over 20, or 17x to the 21 over 21.
Yeah, there we go.
Yeah.
Plus c.
Plus c. There we go. All right, great. We are living the dream here, the antiderivative dream. So on the bottom of page 322, there are some great pictures about what this looks like, where we get a family of antiderivatives. So let's go ahead and do something real basic. So the antiderivative, well, I guess we could go with our friendly little 2x is equal to x squared, 2x squared over 2 plus c. So it's going to be x squared plus c. Let's think about what this is. If we call this f of x, and our integrand, remember, is sort of like our derivative, let's think about what those would look like graphically. So I'll draw this. We'll start off with the derivative, f prime of x. What does f prime of x, which is, like I said, always the integrand here, what does 2x look like?
A line.
Looks like a line.
Going through this origin.
Yeah, it goes to the origin. All right, there it is. 2x. Now this family of functions that we have here, x squared plus c, what that means is we could have x squared plus 0, which would be that parabola. We could have x squared plus 1, which would be that parabola. You could have x squared plus 2, which would be this parabola. We could have x squared minus 1, which would be this one. X squared minus 2. But what's really interesting is that for all of those guys, the derivative of all of them is 2x. So, we're kind of going the opposite direction on that. On your in the book, they kind of give some other examples, but I feel like this picture is actually really a lot better. So. Okay. What else can we say? I need to go backwards in human. Paula, does that make sense?
Mm-hmm.
You get all those different.
Yeah, I have it written down.
Yeah, all the plus C's and stuff like that. Okay. I neglected to tell you something. I should have specified that integral, for reasons which will become apparent in the next chapter. This is technically called the indefinite integral. So I'm going to say integral, but that term right there is called the indefinite integral, because we will later find out about something called the definite integral, which definitely has numbers down here and up here, and those have meaning, and we'll see what that's all about.
Yeah,
So,
that was what I was gonna ask. If the definite was the one that had like 2 on the bottom and then 4 on the top.
Yep, it's definite because it's like it's defined. You know, it's got boundaries. Also, you could say this is indefinite. So, your book kind of makes a. If you look on page 323, it says the notation, blah 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 blah. Take the derivative of. Anyway, and then you've got the power rule for indefinite integrals. So I guess we could write the power rule for indefinite integrals. The integral of x to the n dx equals x to the n plus 1 divided by n plus 1 plus c. You probably have that written down on your paper since it was inside a box. But now we know exactly how to use it, and we're feeling pretty good. So moving on to 324. Now that we have this notation and we have this rule, the antiderivative power rule, there are other properties of antiderivatives. We already kind of saw one of them where that constant there. So if you have the antiderivative of, I'm going to say k times some function, some f prime, f prime of x dx, then that's equal to k times the integral f prime of x dx, something like that. You can pull that k out, and the reason is because the antiderivative and the derivative. Anyway, if you have just a constant multiplier, then that's what we get. Technically, I wouldn't really need to indicate that this is the derivative, but I kind of am just for clarity at this point. We also have a sum and difference property of integrals, namely that, you know, if you have the integral of, and I'll put a square bracket here, you know, f of x plus or minus g of x, square bracket, d of x is equal to the integral f of x dx plus the integral g of x dx So real briefly looking at what those mean, the integral of 3x to the 5th dx is the same as saying 3 times the integral of x to the 5th dx, which is 3 times, so now y'all tell me, what is the antiderivative of x to the 5th?
X to the 6 over 6. Which is plus c.
Plus c. Now I'm doing this for a real specific reason. So, because it's 3 times that whole antiderivative, and so I'm replacing that whole antiderivative with this stuff that's inside the square brackets, x to the 6 over 6 plus c. Now, let's go ahead and distribute that 3. When the 3 gets multiplied over here, then it reduces with the 6, and so we have x to the 6th over 2, and then we have plus 3 times c. We're like, okay, 3 times c? Well, what is c? We don't know, but it's a number, okay? And it's being multiplied by 3, which is another number. So this is where mathematicians get kind of almost kind of shady here, but this is what we do. We say, all right, 3 times a number is just going to be another number. So it makes sense to actually put a different letter here, like D or something like that, but we never put another letter. We actually just put C. So you end up, if you think about it mathematically, you say 3 times C is equal to C, which is not correct mathematically yet, except unless C is equal to
0.
1 or 0. No, yeah, 0. But we allow it, okay? 3 times, a constant times another constant is a constant. So there you go. That's kind of an interesting phenomenon. For the most part, though, what we do when we see this right here, we normally just say, all right, 3, and this is what we did a few minutes ago. 3 times x to the 6th over 6 plus c, and then we just do x to the 6th over 2 plus c. That's kind of the way that we did it, and that's the smart way of doing it. But I just want to kind of show you how it was valid. Now applying the sum and difference property, that would be an example like this. The integral of, 4x squared plus 3x dx, where normally that integrand is going to be in parentheses. So all you do is if we wanted to really be pedantic about it, we do the integral of 4x squared dx plus the integral of 3x dx. It's just like, don't mess with all that. Just do the stinking antiderivative here. You know what I mean? Antiderivative of 4x squared is going to be 4x
To the
third
over 3.
over 3 plus
C.
Not okay. Yes, we could put plus c, and then plus antiderivative of 3x
Is 3x squared over 2 plus C.
plus c. Now we're not necessarily guaranteed that this c is equal to that c, so I might call this c1, and I might call that c2, and then I'm gonna write this as write the x terms first. So 4x cubed over 3 plus 3x squared over 2 plus, and you might say, well, that's going to be over here c1 plus c2. We probably should give it another letter, like maybe D or E or Z or who knows what. But mathematicians, once again, get real lazy, and we're like, yeah, this is a constant and this is a constant, so no matter what, when you add them up, you're going to get another constant. It could be anything. So, they just put plus C because it represents a constant. And what we do is when we deal with antiderivatives and we have some sort of polynomial here, we don't even mess with this step. We just go straight from 4x squared, jump down to 4x cubed over 3, and we jump from the 3x to the 3x squared over 2, and with a plus c. Okay? All right. That is a lot of stuff, but definitely manageable. Looking in reverse order, what we talked about today was the sum and difference property of integrals, the constant multiple rule of integrals. We dealt with the constant of integration. We talked about the terms, indefinite integral, the integrand, and then that dx, which is with respect to x. We kind of discovered the antiderivative power rule, which that was cool. We found out that taking the antiderivative gives you multiple answers. We did all kinds of stuff today. All right, I should feel proud of yourself. Okay, so no particular homework on this, because what we're going to do tomorrow is we're going to look at the antiderivative of sine and cosine and tangent and e to the x and all that stuff. And then I'm just going to give you an awesome homework that's going to put all that together. Okay, so super excited about that. You have a few more days. If you haven't taken notes on 5.1, you've got probably till next Monday to take notes on 5.1. Okay? So there's the antiderivative. See you tomorrow.